With problem number 48, we have a different type of problem than normally occurs in many math textbooks. And it is a very interesting type problem because it really makes us think about the quantities and the relationships between different quantities in an equation, which is very meaningful, which will help us to have a deeper understanding of how equations work and what's going on in a particular equation. So the question here is this: as c increases, does the value of x increase, decrease, or stay the same for each equation? And so what I'm going to do then is for each equation, to set up a table of values. So my first equation is x minus c is equal to 0. So I'm going to set up a table of values for c and for x. Now what I'm going to do is I'm going to pick an arbitrary, doesn't matter what the value is, a value for c. And it can be anything. So in the first equation I will pick c, let c be 5. But it could be anything. Now what I'm going to do is I'm going to substitute that in the original equation for c and solve for x. So we know we would add 5 to both sides, and so in this case x would be equal to 5 also. So I'm going to put 5 into the table for x when c is 5. Now what I want to know is, as c increases, what happens to the value of x? Does it also increase? Does it decrease? Or does it stay the same? So what I want to know does x go up from 5, down from 5, or stay the same as 5? So let's pick another value for c, an increased value of c. So let's let c be equal to 6. Although it could be 10, could be 20, anything greater than 5. Let's plug that in to the original equation, and we add 6 to both sides, and we see that x would have to be equal to 6. So the question is not does x stay the same as c? That's not the question. The question is, as c goes up from 5 to 6, does x go up, go down, or stay the same? And we can see that x goes up, so we'll say that the value of x increases when the value of c increases. Okay, so that's how that's going to work. We're going to go on to the second example now. Cx is equal to 1, and we'll use a different color here so we don't get those confused. So our original equation is Cx is equal to 1. We'll make a little table for c values and x values. We'll pick an arbitrary value of c, doesn't matter what it is, and let's say that that is equal to 2. We'll plug that in. 2x is equal to 1. We know we solve this by dividing both sides by 2, so x would be equal to 1/2 in that case. Now let's pick an increased value of c. So remember, this is our original equation, just as this was our original equation in the first part. Now we want to pick an increased value for c. Let's just say that's 3. We'll make a new equation. 3x is equal to 1. Divide both sides by 3 in this case, so x is equal to 1/3. Now the question is, when c went up from 2 to 3, did x go up, go down, or stay the same? And to answer that question, we'll have to know whether 1/2 is more than 1/3, less than 1/3, or the same as 1/3. And so in this case, we would have to say that we go down from 1/2 to 1/3. And so in this particular case, the value of x decreases as c increases. Hopefully that's clear. Okay, then we'll go on to the third example, which is Cx is equal to C. We'll make a little table of values again for C and X, and we'll pick an arbitrary value of C. So let's say C is equal to 10. Then let's see what happens here. So if we have 10 times X is equal to 10, we'd have to put 10 in both places where C is. And then to solve that, of course, we divide both sides by 10, and we'd end up with X is equal to 1. So when C is equal to 10, X is equal to 1. Let's pick an increased value of C. For example, C is equal to 15. Plug it in for C in both places in our original equation, and we'd get 15x is equal to 15. Divide both sides by 15, and we have x again is equal to 1. So what happens as C goes up from 10 to 15, x stays equal. X is the same. So we would say here then that x stays the same. All right? Okay, now for the final example, which is x over c is equal to 1. Once again, we make a table of values for c and x. We pick an arbitrary value for c. Once again, arbitrary meaning that it doesn't matter what the value of c is. So let's say that c is equal to 20. When we plug in c is equal to 20 into our equation, we now have the equation x over 20 is equal to 1. To solve this, since we're dividing by 20, the reverse operation would be to multiply both sides by 20, and when we do, we end up with x is equal to 20. Okay, so we need to pick another value. Let's let c be 30 this time. So we plug that back into our original equation, which would then be x over 30 is equal to 1. Multiply both sides by 30, and we get x is equal to 30. So the question then is, as c went up from 20 to 30, did x go up, go down, or stay the same? The question is not, is x the same as c, which it is, but the question rather is, does x increase when c goes from 20 to 30? Did x go up, go down, or stay the same? And the answer is that x also went up. So we say x increases as c increases. So these are very important ideas in analyzing the relationships among quantities in a particular equation. And we'll see more problems of this type, I'm sure, in different sections and chapters throughout the book. What we're looking at here are examples of simple equations that we've been working with actual values for c in them. But here we're analyzing, again, as I said, the relationship between different quantities in the equation, and what happens as one of them goes up. Does the other quantity go up, go down, stay the same, etc. All right.